Hi, good afternoon all. I'm Deepan. I'm doing my third year in PhD in the Department of Geography and Earth Science. My field of work is on electrochemical detection for heavy metal ions. And here I will be presenting one of my work. So here the section includes about the material preparation and characterization and experimental setup and what are the heavy metal ions we are detecting. So why we need to detect heavy metal ions? So it's one of the essential minerals we need for the body, as well as over consumption of this leads to fatal diseases. So, and it's one of the common pollutant in water resources such as even in lakes or drinking water. So because of that, we have to monitor these heavy metal ions, and usually the common techniques like spectrophotometer or other techniques have it's so expensive and it's not easy to carry them across the field. So we developed a low-cost, simple screen printed electrochemical sensors, and I will be talking about that. So what we choose here is graphitic carbon nitride. So it's one of the metal-free N-type semiconductors, and those are biocompatible and friendly to environmental as well. So here, how we are sensing this graphitic carbon nitride is that we are doing thermal condensation and evaporation at 520 and 550 degrees Celsius. What we are doing is like we are using the melamine and getting it heated in the furnace up to 520 degrees Celsius for 4 hours, and later we are ramping up the temperature to 550 degrees Celsius. And through this, like this melamine structure get conjugated and it forms a hexagonal core shell kind of structure. And this is similar to graphene, so we are not using the same metal oxide based detection for heavy metal ions. We are using something which is environmental friendly here. And usually these are highly photoactive, and we are using it for photocatalysis or even optoelectronic devices. So usually these materials are added along with metal oxide based materials to form a electrochemical sensor. So I was curious like what it really senses instead of blending with something else. So I was conducting an experiment. So here like we modified the carbon glassy carbon electrode with the G graphitic carbon nitride, and we are modifying in a way like these layers are getting stabbed up by a single layer instead of a bulk section. So we are drop casting it into multiple times, and the results are like what we do is like we did a CV and DPV, and we found out like uh, for the iron, ferrous ions, it's directing, and at minus 0.09 volt, which is a really less power consumption in case of a sensor device. So at that point, we are sensing ferrous ion, and we did a concentration study like we from 0.9 millimolar to 5 millimolar. We are running a concentration study, and we figure out like the oxidation peak forms two linear range with respect to the concentration. And the first layer is we predict it to be because of this hexagonal core shell structure, which actually like absorbs iron at a really low concentration. So here like it's kind of forming a resistive based phenomena, and after sometimes at a higher concentration it is more focused on diffusion control process. So in order to confirm this, we are running a accumulation study. So what we do is like we run the CV for 2.5 millimolar direction of ion at different scan speed from 10 millivolt per second to 1000 millivolt per second. And here like the second graph and the third graph where we are relating the peak current of the oxidation peak to the scan rate and the square root of the scan rate based on the Cottrell's equation. Like here, both of them show a linear phenomena. So the R square value is more than 0.95 and 0.99. So we are thinking like this involves more the both the absorption and diffusion control process. So at higher concentration, we need this to be diffusion control process in order to show the previous phenomena. So we are running we are plotting the logarithmic of oxidation of P current and logarithmic of scan rate, and we are finding that the slope is 0.55, which is close to ideal diffusion control mechanism, which is like 0.5. And we also did a repeatability test, and we are running it for like 30 cycles, and we are seeing the changes for first and the 30 cycle when compared to the other concentration changes, like for example like 2.5 millimolar to 3 millimolar. This is significantly less, so it's quite repeatable. And later we want to make it into a flexible, easily usable, portable sensor, so we use a screen printer sensor. So here we use screen printing techniques where we coat carbon layer up to like 20 times. So at the end, like all these electrodes are made of carbon electrodes, and the working electrode is modified with graphic carbon nitride, and we run a CV, DPV, and square wave voltammetry technique for these screen printer sensors, and we also found that it can detect cobalt ions at lower concentration, so around like 1 millimolar to 1000 millimolar. So we use this technique, like if it's higher concentration we can go for cyclic voltammetry, and if it's a lower concentration we can go for DPV, and if you want an instant result we can go for square wave voltammetry. And that's all. So feel free to ask any questions if you guys want.